this, let's look at it in real life. We're going to do this lab when I return next week, probably Thursday or Friday. And what we'll do is, this is showing you some liver. If you're not a fan of liver, don't come next Thursday or Friday. Smells kind of weird. But with this liver, we have liver homogenate, which is just basically a blenderized mixture of liver. And you'll see that it says catalase enzyme. So we have some enzyme in here. On the left in this jar, we have some H2O2, which is hydrogen peroxide, which is our substrate. This is one of our reactants. You'll see that when we run the reaction on the left side, the enzyme without the substrate, we don't get a reaction. There's nothing happening. You can just see the liquid just resting there at the bottom. On the other hand, when we run the enzyme with the substrate, that piece that needed to come in to our protein, go back. If we had our protein that looked like this or something and had that kind of circular area where the substrate needed to come in and bind in order for our enzyme to work, when we add that substrate, the enzyme is actually going to be able to catalyze the liver. And in this case, we see the reaction running, and we know it's happening because we get products. Specifically, we get H2O and O2. The way we see that oxygen is, notice this is all bubbly. And so by seeing oxygen and water, the water being also in the bubbles, we can see that there have been products made. This shows us, if we go back to our graph, that we've reached the end of the reaction. In the previous one, nothing's happening. We see no bubbles, we see no water, and the reason for that is because we didn't reach high enough activation energy. Because it took too much energy. We would probably have to heat this up. Maybe we'd have to put some kind of pressure on it in order to force the reaction to occur. But in the presence of the enzyme, just sitting there at room temperature, it's able to run the reaction. Okay, so now we've kind of introduced the idea of what it takes for the reaction to occur. Now we're going to go into some more detail here. So we use the word substrate, we use the word enzyme. Now let's talk about the enzyme-substrate complex. When we talk about the substance, the reactant, that's the thing that is reacting. The enzyme that acts on it is the substrate. So when the enzyme is present, we're going to have that reaction. It's hopefully going to run based on some substance present. And as it says, the substance an enzyme acts on is the substrate. So we have a picture here. This is our enzyme. Remember, we said that it's usually going to be represented by some kind of big squiggly thing. Three-dimensionally, it might look like this. And we have this kind of hole here, which you can see right here. And this one, notice, is kind of square-shaped. So in theory, we need some substrate, which would be shaped kind of like that hole, to come in, join with the enzyme, and allow it to start actually doing its job. By doing this, when we have this shaped area and we have some substrate that's going to come in and bind, we have what's called an active site. The active site simply means it's this kind of area, this restricted region on an enzyme, which is going to allow binding to occur to the substrate. So you can kind of think of it as almost a lock and key. We have this lock, which is the enzyme, and the key is going to be the substrate that comes in and it binds to that. So notice here we have our key, it's coming in and it's unlocking the potential for this enzyme to run the reaction. Let me go back here for a minute. So we have our active site here, and I would actually recommend in your notes, go ahead and draw that. Just draw kind of a big blurby looking thing and try to make that pretty well shaped and label it active site, just like they've done below. Then notice we have the substrate and it comes in and it can fit perfectly right in there. So you could label that then the substrate. So active site is restricted region of the enzyme which binds to the substrate. Again, the lock and key method is what you'll a lot of times hear it called. When we get into this idea of lock and key, something that's going to show up probably on your STAR test is going to be the idea of induced fit. When we say induced fit, what that means is when the substrate comes in and binds, it's easier to just show this. Go back. it's going to change the shape of the enzyme's active site. What we mean by that is, as the word induce might suggest, the presence of the substrate is going to cause or induce a change in the enzyme. Later on, we'll get into more ideas in terms of this active site and why it's important, and we'll see that some changes can make it so that the enzyme can't work anymore. We might have something try and come and get into this active site to block whatever substrate might be trying to get in there. We might have something binding somewhere else on the enzyme to change its shape. But the idea with induced fit is that it's a change in shape of the active site, which is actually induced by the substrate itself. So to make that a little more clear, it's a change in truly the configuration of the enzyme's active site. What's actually happening is we have some hydrogen bonding and some ionic bonding involved, and when that happens, we're literally going to change the shape of the entire enzyme. We have our substrate coming in, the active site's going to kind of join with that substrate, and now we have a complete enzyme. It's changing shape a little so that the enzyme can start to function. This is going to be a good stopping point for this part, and so the next part we're going to get into more ideas in terms of how the actual enzyme works and some factors that can affect whether or not it functions properly.